Hello and welcome to the presentation of the Persis paper, a Persian phone recognition pipeline using convolutional neural networks. I am Mehrdad Mohammadian. It's a research with the cooperation of Islamic Azad University and Linnaeus University. Imagine you are a graphic designer that finds an interesting design project somewhere, maybe on the internet, and probably you like the used font in the image, but you don't know its name, and you wish there was a service to recognize the font of this image. In this situation, visual font recognition or VFR can help you. In general, a VFR system can assist graphic designers to identify the font typeface in an image. Besides, there is another application. VFR systems also aid in improving the speed and accuracy of optical character recognition or OCR systems. In this paper, we proposed a font recognition pipeline called Persis for the Persian language. Why the Persian language? Why do we need to propose a method for Persian font recognition? Well, according to the World Wide Web Technology Survey's website, in 2021, Persian was the fifth most common language on the web. Therefore, it is important to develop new algorithms to understand Persian in a variety of fields. Recent works in Persian font recognition can only handle one text level. In fact, font recognition can be used in different text levels like word, line, letter, or block of text. Also, recent works used traditional feature engineering methods like histogram of oriented gradients, scale invariant feature transform, and Gabor filter. These methods focus on building features using raw input samples, and to perform classification, they feed these handcrafted features to a machine learning algorithm like support vector machines, k-nearest neighbors, or multi-layer perceptron. As we know, these handcrafted features have problems like generalization. Recent works never used new techniques like deep learning. In conjunction with methods, the datasets used in recent studies also have a lot of limitations. The samples are analogous with any consideration of challenging conditions such as different backgrounds, text colors, text position, and etc. Additionally, the number of supported fonts in recent works is insufficient for the font recognition task. The methods proposed in recent papers on Persian font recognition need to use a number of pre-processing steps like feature extraction, binarization, normalization, and etc. Another fact about PFR is its difficulty. In general, there are 114 different letter forms in the Persian alphabet. As we know, Persian alphabet has 32 letters. Some letters have an additional component, which may be a dot, a group of dots, or a slanted bar. Additionally, letters can appear in final, initial, medial, and isolated forms, and also in both printed and handwritten documents. Persian script is cursive. As a result, the cursiveness and these characteristics of Persian language make it more difficult to recognize compared to Latin. Here we have our proposed method for solving the Persian font recognition problem. As you can see, it includes two parts. In part 1, we do an image segmentation using a CNN model and then feed its output to the next part, which is an image classification using another CNN model. Also, the output of part 1 can be used for a text extraction service. Before going into the details of the method, let's look at the datasets. As you can see in this figure, The samples of previous datasets are not different in light conditions, text colors, text positions, and backgrounds. To be exact, the text color of all samples in recent datasets is black, the background is white, and the position of the text in the image is too similar. These limitations can't help us to build a robust and flexible font recognition system. In addition, previous datasets are not publicly available to the community. To fill this enormous gap in existing datasets with more challenging samples for Persian font recognition, we propose two datasets: the Persian font recognition or PFR for the classification part and the Persian text image segmentation or PTI-SEG for our image segmentation part. These datasets are available in GitHub repository of the paper for future works. Also, we provided our data generator algorithm in the paper. For generating the PTI-SEG dataset, we used 735 different backgrounds in 4 types of stock, papers, noisy real world, and texture, and apply 4 effects: gradient light, folding, subtle noise, and ink blend. As we know, real world images can be different in light conditions. Therefore, we applied the random gradient light effect to images for simulation. Because many images can have noises and ink bled from pen around the text, we used subtle noise and ink bled for these situations. Also, some images can be like folded book paper. The folding effect is applied for this reason. The PFR and PTI-SEG are both generated at 4 text levels: black, line, word, and letter, and 60 font typefaces. The shape of the image in these two datasets is 224 in 224. As I mentioned before, it is our pipeline to solve the PFR problem. Both of our models are based on convolutional neural networks. We used deep learning, which is one of the well-known machine learning algorithms. Deep learning methods are based on representation learning. These methods automatically learn the features which are not engineered by humans to be used in classification or detection tasks. This figure shows the architecture of our image segmentation model. The primary goal of image segmentation is to make images more simple and meaningful to our classification part. Image segmentation can make images smooth and easy to evaluate. In addition, it can help to find the region of interest. We use a unit shape model, which is an encoder-decoder CNN. The unit is a fast and accurate image segmentation CNN model, which won the ISBI Cell Tracking Challenge in 2015 by a great margin compared to the other models. All convolutional layers have a 3x3 kernel with a ReLU activation function. In this part of our pipeline, we have a binary image segmentation problem with 2 classes, including the background in black and text in white. Therefore, for loss calculation, we use the binary cross entropy loss function. For the evaluation of the segmentation part, we used intersection over union with 50 and 75 thresholds and dissimilarity coefficient. We split the PTI-SEG dataset with 10K samples into 3 parts. During the training, 80% of the PTI-SEG samples are used for the train set and 20% for the test set. For weight optimization of image segmentation model, we use the Adam optimizer. Here are the results of the image segmentation model on the PTI-SEG test set. This figure shows the architecture of our image classification model. As you can see, we use a global average pooling or gap layer instead of the fully connected layer to reduce the model parameters. By using gap, we don't need to use fully connected layers and it can help to reduce the number of parameters of our model. Another advantage of GAP is that it has no parameters to optimize, so it can help to avoid overfitting in this layer. Like in the image segmentation part, we split the PFR dataset for training the classification model. Data augmentation is applied to prevent overfitting problem with the same conditions in the image segmentation part. All convolutional layers have a 3x3 kernel with a ReLU activation function. For weight optimization, we use the Adam optimizer. We tested our pipeline in 4 different ways, testing the entire pipeline on 2 public available datasets for Persian OCR and Arabic font recognition, using the grayscale images that resemble example of previous datasets, comparing the speed of our entire proposed pipeline and the recent studies, determining the parameters and floating point operations or flops for our pipeline. Flops describe how many operations are required to run a single instance on a deep learning model. We use the KAFT dataset for testing, which is the dataset for Arabic font recognition. As we know, alphabet and writing systems of the Arabic and Persian language are remarkably similar. The original KAFT is an enormous dataset with about 2.5 million samples, and its images exist in 4 resolution levels with the same content. Therefore, we use a smaller version of the KAFT dataset, which has about 6,000 samples in 11 classes. All images are in line level and 100 dpi resolution, which is the lowest quality in the dataset. The next dataset is IDPL-PFOD, which is a dataset for Persian OCR research. It has 11 classes with about 3,000 samples. This dataset is created with more challenging conditions in comparison with the previous dataset in PFR. As I mentioned before, all samples from the recent datasets in Persian font recognition are in grayscale. We tested our pipeline using the grayscale version of our new datasets. In this experiment, we trained our image segmentation model with the PTI-seg dataset samples that are converted to grayscale. Then we trained classification model by using the output of the image segmentation model. In this experiment, we compare the time performance of our proposed pipeline with recent studies. Recent studies are not directly comparable because most of these papers report time only for the feature extraction steps, while our pipeline, based on the CNN models, is free of the feature extraction steps. In addition to time, we mention processors and environments in recent articles. All reported times are for one sample, and both the feature extraction and the whole process columns are in seconds. For a better comparison of future studies with our work, we report flops and the number of trainable parameters. The total number of flops and the total number of trainable parameters for our pipeline is about 8 million. To sum up, we propose the first public datasets for PFR, and for the first time we proposed a pipeline with CNN models to solve PFR. Top 1 accuracy in our datasets is 78, in IDPL PFOD is 89.1, and in KAFT is 94.5. Furthermore, the average time spent in entire pipeline for one sample of our proposed dataset is 0.54 and 0.017 seconds for CPU and GPU respectively. Thank you for your time. If you have any questions, please contact us.